similar. But, I mean, the problems are slightly different, but you're doing something similar in both of the problems. You have a body of water, and you're trying to pump out the water. And in number 4, the height of the pool is 5 feet, so the water that is down here has to move a full 5 feet. The water that's here only has to move 1 foot, because in the problem it tells you the water depth is 4 feet. So the water that's at the top is only having to move 1 foot. The water that's at the bottom has to move all 5 feet. The water in the middle is going to move some intermediate amount. So you want to picture moving layers of the water. I mean, even though you're,
Not if the sump
in
pump's in the
terms of,
bottom.
wait, what?
Not if the sump pump's in the bottom.
I know, but our pump, again,
Our
I
pump
got the
travels.
problems out of the book.
Come
Our
on
Pumps,
now.
it's a surface pump.
Yeah,
It's a surface pump, yes, it is a surface pump. Okay, so you want to picture you're moving layers of water. So your volume of water is a pi r squared times a little a thickness, okay? So you're, I'll put a delta x to mean some sort of thickness. So you're imagining skinnier and skinnier slices of water. The radius of this particular pool is 12, so 144 pi times some little thickness is the volume of the water. But we're not moving volume, we're moving force. And so the weight of the water is the density of the water times the volume of the water. And that's going to give us the weight. Weight is density times volume. So density of water is 62.5 pounds per cubic foot. Okay, so we're working in feet. So for any cubic foot, I mean, a cubic foot of water weighs a lot more than you think it is. I mean, picture a box that's
8
a foot
pounds
by
a
foot.
gallon.
Yeah, that's right, 8 pounds a gallon. So 62.5 pounds is gonna multiply your 144 pi. And again, this is just representing some minuscule thickness. All right, so that's giving you your force. So my force is all of this stuff multiplied together. And the delta x is going to be represented by the dx, but then the distance, okay, the one problem we did, the dx represented our distance. Here, it's part of my volume. The distance that's really part of the whole function is represented by a linear equation that's tracking the distance as you move from 1 foot down to 5 feet. So I think I would just put x, okay? So I've separated it from the rest of this other stuff only because this is representing your distance. The dx is really part of your force. And then my distance is going from a low of 1 foot to a high of 5 feet. And if you clean that up and work it all out, we end up getting
108,000 foot-pounds.
108,000 foot-pounds. Okay, or is that, what's a pi in there? Hang on. You know, I think it looks like the pi might have gotten mixed up. 9,000. Well, no, 9,000 times 12. Yeah, you got that. There should be a pi on the end of that. It's 9,000 times 12 times pi, so it should be 108,000 pi foot-pounds.
How do you set a torque wrench to that?
Wait, how to what? Okay, so number 5 is kind of similar, but instead of it just